Over NBC's coast-to-coast network of independent and affiliated stations, the University of Chicago Roundtable. We present Harold C. Urey of the Department of Chemistry of the University of Chicago. Mr. Urey.
Is there life on other worlds besides our own? Are there other worlds like our own Earth? What are the conditions on other planets? And what are the conditions which are necessary for life?
The University of Chicago Roundtable grew out of arguments held by professors at the faculty club. In 1931, they were convinced their forum would make for good radio. WMAQ agreed. The show premiered on February 1st of that year. It began running nationally over NBC on October 15, 1933. The 30-minute time slot allowed for little grandstanding. Professors rotated with each broadcast according to their expertise.
Even of the simplest forms. For example, simple green plants.
If people really were seeing UFOs in the sky, they had to be coming from other worlds. On December 19, 1948, the Roundtable attempted to answer the question from a scientific point of view.
I wish to introduce our speakers today. They are Professor Gerard P. Kuiper of Yerkes Observatory and McDonnell Observatory in Texas, who has recently been making some very interesting studies on the character of the light that is reflected from the planet Mars. Professor H. Gaffron, biochemist, professor at the University of Chicago, who has been studying the photosynthetic process. That is the process by which light is absorbed by green plants and used as a source of energy for the production of all the compounds that are produced by plants. In this, he is making use of the isotopic tracers. Professor Harrison Brown of the Institute for Nuclear Studies at the University of Chicago, who during the last few years has been investigating the isotopic composition, or the chemical composition of the meteorites, these small bits of matter that come to us from somewhere outside our own Earth. Professor Kuiper, is the system of our sun and planets the only one of its kind in the universe, or are there others?
Well, Urey, we do not know this by direct observation, because if the nearest star had planets like our own sun has, we would not be able to see it. We wouldn't be able to see them. However, we can say this. Only recently, the theory of the origin of the solar system consisted of the assumption that a foreign star came close to the sun, pulled out a certain amount of surface material, and that this surface material condensed into the planets. Such an event would be extremely rare, and if this theory were correct, one might assume that our own planetary system were probably unique in our whole galaxy of stars. However, recently we have become convinced that the planets probably originated by condensation from a cloud of gas surrounding the sun, and the likelihood of the presence of such a cloud of gas, of the total mass of the planets, may be estimated to be perhaps 1 part in 1,000 for any particular star occurring. Therefore, as we now see it, we would estimate planetary systems to be rather frequent in space.
Well, let's see, how many stars are there? There's first, how many stars in our own galaxy?
The total mass of the galaxy is known, and we know about how much each star weighs. Therefore, it is possible to compute the total number of stars in our galaxy, and this turns out to be a 1 with about 11 zeros after it. In other words, 100 billion stars in our own galaxy. But that is not all. Outside our galaxy, we have enormous numbers of outer galaxies, sometimes called extragalactic nebulae, and the surveys which have been made at the Mount Wilson Observatory in California have extended to a distance of about 500 million light years. That means that from the boundaries of the visible space, it takes the light 500 million years to reach us. Within this enormous volume, one has approximately 1 billion galaxies, so that the total number of stars within the visible universe may be estimated to be a 1 with 20 zeros after it.
And of these, 1,000 of them may have planets about them of approximately the kind that we find in our solar system. That is, 1 with 17 zeros after it is the number of solar systems to be expected. A very, very large number indeed.
I think, Yuri, that is correct. That is certainly the best estimate we can make today.
And of course, we see that this may be the number of such solar systems. How about the chemical composition? Brown, you've been working some on this question of chemical composition of matter outside of the Earth.
One of the more remarkable features of our own solar system, Yuri, is the similarity in composition between our Earth and the other planets and our own sun. Most people believe that the Earth is vastly different in composition from our sun, but that is not true. Actually, with the exception of the very light elements, such as hydrogen and helium and carbon and nitrogen, the relative abundances of the various elements in the Earth appear to be just about the same as the relative abundances of those same elements in the sun. Similarly, it has been found that the composition of meteorites is quite close to the gross composition of our Earth and to some of the other planets, such as Mars and Venus, at least with respect to these heavy elements. By heavy elements, I mean iron and silicon and magnesium and calcium, elements such as that. Now, one can go to the larger planets. There, they are so large that they retain large quantities of hydrogen and helium, these very light substances. But even there, the gross composition, including the light elements this time, appears to be just about the same as the composition of those elements in the sun. I believe, Kuiper, is it not true that the other stars in our own galaxy and in the extra galactic nebulae have compositions which are quite close to our own sun, too?
Yes, Brown, I think that is one of the most interesting results of astronomy, that the composition of one star compared to another star is so remarkably similar. There may be differences, perhaps, of a factor 2 in certain abundance ratios, but by and large, we can say that the stars have practically the same composition as the sun, and if we observe the spectra of the distant galaxies, we get again a spectrum very similar to the spectrum of the galaxy as a whole. In other words, within the whole visible universe, we must assume that the same elements of the periodic table occur and in approximately the same ratios as they do here.
And is it not true that these stars and our own sun are composed largely of these lighter substances like hydrogen and helium and oxygen and so forth?
Yes, they are the most abundant of the elements. That's correct.
Well, now, there may be many places then like the Earth. What are the other factors? What are the factors that are necessary for a planet to be suitable for life? What size, what temperature, what other things? Gaffron, could you, as a biochemist, tell us something about this?
Well, in contrast to the overall similarity of matter in the universe, the conditions under which life appears on Earth seem rather restricted. For instance, the temperature range is rather small. It's between the boiling point of water on the one end and a few degrees below the freezing of water where life really can thrive. Many organisms cannot stand more than about 120 degrees Fahrenheit. Some simpler plants can live in hot springs, have been found living at 160 degrees Fahrenheit or even above. On the other hand, the cold does not destroy plants or simple life very easily. And we have, of course, in the form of seeds and spores of bacteria, forms which can last for many, many years. It come to active life again.
There were no scripts, but Roundtable was the first show of its kind to be issued in a weekly magazine. It contained a transcript of the previous program, biographies of the participants, listener feedback, suggested topical reading, and a schedule of coming broadcasts.
The conditions are suitable for life part of the time.
The University of Chicago Roundtable would air until June 12, 1955. It finally went off the air when NBC launched Monitor.
Exist and wait for a better time to become active again.
Oh, yes, you could have a living season, so to speak, which would be much shorter than on the Earth, but low temperatures as such would not speak against it. But another restriction is the presence of water. And most living things contain 80 to 90% water, and if desiccated, they die, except again if adapted to survive in the dry state. And such rusting organisms can continue come to active life again when moistened. Otherwise, they would stay dormant for many years.